Hello, welcome to Understanding Power Electronics. In this video, we will see the complete characteristics of the boost converter in continuous conduction mode, in discontinuous conduction mode, and in the boundary between the two modes. We will see how, when the complete characteristics are plotted together, meaningful insights arise. We will also go through an example which uses the complete characteristics. With those as our aims, let's get started. Here is a boost converter. For the purposes of this video, we will assume ideal operation of the boost converter. What are we going to learn? First, we will go through an overview of the continuous conduction mode, discontinuous conduction mode, and boundary operation to set the stage. Then we will look at the CCM-DCM boundary curve and understand it in greater detail. Then we will put it all together in graphical form, the CCM, DCM, and the boundary, and discuss some important properties of the boost converter when viewed as a whole. Lastly, we will do an example based on inductor value selection. There are some earlier videos which you might find useful. One, the boost converter CCM operation 2B-1, 2B-2 boost converter, the boundary operation, and then 2B-3 boost converter DCM operation. You may wish to go through them to gain a better understanding of the boost converter basic operation. In plotting these characteristics, we are going to do some normalization. That means the current and voltages will be divided by certain constant current and voltages so that the equations will become dimensionless. The number of variables in the equations will go down. It will be easier to plot, and the whole converter operation and the plots will be more meaningful. This is something that is often done in engineering and science. The normalization that we are going to do may be called base V0 normalization. This normalization is useful when the output voltage is to be regulated. The voltage normalization factor is V0, the output voltage, which is taken to be constant here. Through closed loop regulation, we are regulating the output voltage constant. This is true or mostly true in many applications. In, the current normalization factor, is V0 Ts by 2L. That's a factor that appears in the current equations, and we can get rid of that by choosing that as the current normalization factor. All voltages in the circuit can be divided by Vn, that is V0. All currents in the circuit can be divided by In, that is V0 Ts by 2L. So if you have a voltage Vx, then Vxn is Vx by Vn, that is Vx by V0. The voltage variable now becomes a dimensionless, unitless variable. Notice that V0 is treated as constant. So Vxn is directly proportional to Vx. Likewise, if you have a current Ix somewhere, then Ixn, the normalized current variable, will be Ix by In, that is Ix by V0 Ts by 2L. V0 Ts by 2L has dimensions of ampere. You can check it out. So Ix by In is again a dimensionless quantity. Once the design is complete, V0, Ts and L are fixed. So In will be a constant value. So we are dividing the Ix by a constant current In. So Ixn, the normalized current variable, is proportional to the actual current Ix. Now we will review briefly the operation of the boost converter under CCM, under continuous conduction mode. The switch is switched on and off at a particular frequency. T on is the on interval, T off is the off interval. All the components are treated as ideal in our discussion. We will see a few waveforms and go through the operation using these waveforms. Vs is the voltage across the switch. When the switch is on, Vs voltage will be 0. It's an ideal switch. And when the switch is off, the diode will be conducting. So the switch voltage will be equal to the output voltage V0. V0 is assumed to be some steady DC voltage. Next, we will see the inductor voltage. The inductor voltage is as shown. When the switch is on, the inductor is connected to the source V in, and when the switch is off, the diode conducts and the inductor voltage will be V in minus V naught as shown. And this inductor voltage is applied to the inductor, and so the inductor current wave shape will depend on that voltage. So the inductor current is as shown. Because the operation is under CCM, the inductor current stays above zero throughout the cycle. Starts from some value I1, goes to I2 at a slope of V in by L. V in is the voltage applied across the inductor, so the slope up is V in by L. And then when the switch is off, the diode conducts and the inductor current falls at a slope of V in minus V naught by L. V naught is higher than V in, so V in minus V naught by L is a negative slope. Because we are assuming that the operation is under steady state, the current returns to the same value I1 as we started with. Now this is the inductor current waveform, and the average of the inductor current waveform is the DC input current. So the DC input current In equals IL average. Capital I indicates the DC current. Now this part of the inductor current is the switch current. This part of the inductor current is the diode current. We can plot the diode current separately as shown. The DC part of the diode current flows through the load. The ripple part is absorbed by the capacitor. So I naught, the output DC current, equals ID average. The operation under continuous conduction mode has been discussed in greater detail in the video 2B-1 in this series. You may wish to go through it in case you want to understand more deeply. Using volt-seconds balance or by any other method, we can derive the equation for the voltage ratio, output voltage to input voltage equals 1 by 1 minus D. Because we are assuming ideal operation, there is no power loss. So V naught I naught equals V in I in. So V naught by V in equals I in by I naught. This is the very familiar boost equation. You can see that the output voltage will always be higher than the input voltage. We can plot V naught by V in terms of D. D will range from 0 to 1. When D equals 0, V naught by V in is 1. As D goes towards 1, V naught by V in curve goes higher and higher. In practice, because of losses in the circuit, there will be an upper limit on the V naught by V in ratio that one can obtain. As I explained earlier, we will be normalizing these equations. Vn is the normalizing factor for voltage that is equal to V naught. We are using the output voltage as the normalizing factor. So the voltage that can be normalized in this equation is the input voltage. So V in by V naught is V in N, that is the normalized input voltage that equals 1 minus D. Another important parameter under continuous conduction mode is delta IL, the peak-to-peak ripple current, that is I2 minus I1. And we can show easily that delta IL is V in Ts by L times D. In terms of V naught, delta IL will be V naught Ts by L D times 1 minus D. One point to be noted is that under CCM, V naught does not depend on the load current ideally. Practically it will, but ideally it won't. Likewise, the ripple current delta IL is V naught Ts by L D times 1 minus D. It does not depend on the load current. Now as we reduce the load current, at some value of the load, the converter will operate at the boundary between CCM and DCM. Under that condition also, the switch voltage will remain the same as in the CCM case. When the switch is on, the switch conducts, the switch voltage is 0. When the switch is off, the diode conducts and the switch voltage will be equal to the output voltage V naught. Likewise, the inductor voltage will toggle between V in and V in minus V naught. IL waveform is as shown. Notice that the wave shape remains the same as in the CCM case. Delta IL is the same. The inductor current returns to 0 at the end of the cycle and immediately rises when the switch is switched on again. Current starts from 0, goes up at a slope of V in by L, goes to the peak IP, And then when the switch is switched off, the diode conducts and the current falls at the rate of V in minus V naught by L and reaches 0, and immediately the switch is switched on and the current goes up again. This is the boundary inductor current. This part of the inductor current is the diode current. When the switch is switched off, the diode starts conducting and the diode current starts from IP and falls to 0 at the end of the T-off interval. The inductor voltage waveform is the same as that in the CCM case. So applying volt-seconds balance, we will again get the same voltage ratio. V naught by Vin equals 1 by 1 minus D, and V in N, the normalized input voltage, is V in by V naught equals 1 minus D. The input boundary current, that is the input current under the boundary condition. That will be the average of the inductor current. So In, the input DC current, equals In B, the boundary input current, equals IL average. So In B is IL average, and that is equal to V in TS by 2LD, basically delta IL by 2. The average of the diode current is now the output current. In this case, it is the output boundary current IOB. So IO equals IOB equals ID average. Since we are assuming ideal operation without any power loss, the input power must be equal to the output power. So the boundary output current must be the input boundary current times V in by V naught. And V in by V naught is 1 minus D. So this will be V in TS by 2L D times 1 minus D. This is the boundary output current. If the load current is above this, you will have continuous conduction mode. If it is less than this, you will have discontinuous conduction mode. Notice that we have the factor V in TS by 2L, whereas we are going to use V naught TS by 2L as the normalizing factor for current. So we can multiply and divide this term by V naught. So if we do that, I naught B is V naught TS by 2L D times 1 minus D whole square. V naught TS by 2L is the normalizing factor for current. So I naught Bn, the normalized boundary current, is I naught B by In. So I naught Bn will be D times 1 minus D whole square. Notice that V in N is 1 minus D. So we can substitute for D in terms of V in N. Then we will get I naught Bn is 1 minus V in N times V in N square. We will use this equation later in this video, so we have highlighted it. There is an earlier video dealing with boundary current 2B2, which deals with the boundary current operation in greater detail. You may wish to go through it. Next, we will plot this equation V in N versus ION. V in N is the input normalized voltage, V in by Vn. Vn is a constant, that is V naught here. ION is I naught by In, where In is V naught Ts by 2L. Essentially, we are plotting the input voltage versus output current when the output voltage is maintained constant. This is a polynomial and it has the shape shown. When the current is greater than the boundary current, we are under continuous conduction mode. So this region will be the CCM region. When the current is less than the boundary current, the operation will be in DCM, and that is this region. Now consider operation at a particular output current. Given a design, In is a constant value. So this vertical red line is under constant current operation given the normalizing factor In as constant. Simply indicates that along that line, the load current is the same. Now consider one operating point here. As you can see, this is in the CCM region. The operation is under continuous conduction mode. And the corresponding V in N is 0.9. That means the input voltage is 90% of the output voltage. If the output voltage is 100 volts, the input voltage will be 90 volts. Now let's reduce the input voltage. The input voltage to output voltage ratio now is 0.6. From 90 volts, we have reduced the input voltage to 60 volts. The current is maintained the same. The output voltage V0 is the same. That means that while the input voltage changes, the duty cycle has been changed correspondingly so that the output voltage has been maintained at the same value. That's what we are assuming. Here, as we can clearly see, the operation is under DCM. As the input voltage is reduced, the operation has shifted from CCM to DCM. Now, let's reduce the input voltage even more. So here, the input voltage is 20% of the output voltage. So if the output voltage is 100 volts, we are having 20 volts as the input. The duty cycle has been again changed by the control system so that the output voltage is maintained the same, 100 volts in our example. So here you can see that the operation is once again in CCM. So with constant V0, holding the load current constant, if the input voltage goes down, first it changes to DCM from CCM and then changes back to CCM. It's like going from one town to another town in a country, but in between we are crossing the border into a second country. This aspect of boost converter, the weird shape of the boundary current, that has to be taken into account if you are designing the boost converter to stay only in CCM or to stay only in DCM. We will be going through an example towards the end of this video addressing precisely that. Next, we will find the maximum boundary current IOB max or IOBN max if we are talking of the normalized values. That is the current and other values at this peak point. This is the boundary equation in normalized form, base V naught normalization. We need to differentiate this and set it equal to 0 to find the maximum boundary load current. So differentiating DIOBN by DVNN, you will get this. One solution is V in n equal to 0. If you set V in n equal to 0, this equation will be 0. So that represents this minimum point. We are not interested in that. The other solution is V in n equal to 2 by 3, that is 0.667. Since V in n equal to 2 by 3, D is 1 by 3. That means the input voltage is 66.7% of the output voltage and the corresponding duty cycle is 1 by 3, 0.333. We can then plug in V in n value into this equation to find IOBN max. If we do that, we will get 0.1481. So the maximum boundary current, the normalized value, is 0.1481. We will use the values V in n, D and IOBN corresponding to IOBN max point M later in the problem. I have highlighted them here. Next, we will revise the discontinuous mode of operation briefly. There is a video 2B-3 in which this mode of operation has been explained in greater detail. You may wish to go through it. We are going to see the waveform under DCM operation. This is the VS waveform or the switch voltage waveform. When the switch is on, the switch voltage will be 0. We are considering ideal switch. And when the switch is off, diode conducts. So the switch voltage will be equal to the output voltage, V0. But the diode does not conduct throughout the off interval in DCM. So when the diode stops conducting, the switch voltage will become equal to V in. So in this part, the switch voltage is V0. In this part, the switch voltage is V in. So the T off interval is split into two sub-intervals, TF, the current fall interval, and TD, the discontinuous interval. The inductor voltage will also show corresponding changes. This is the inductor voltage waveform. When the switch is on, the inductor voltage is V in. When the switch is off, for the TF interval, as long as the diode is conducting, the inductor voltage is V in minus V0. When the diode is also off during the TD interval, there is no inductor current. There is no induced voltage in the inductor. So the inductor voltage will be 0. The inductor current can now be plotted. The inductor current starts from 0, and when the switch is switched on during the T on interval, it goes to a peak of IP at a slope of V in by L. And when the switch is switched off, the current falls. V in minus V naught by L is the slope, and it reaches 0 at the end of the TF interval, the current fall interval. And that's when the diode switches off. Then the inductor current stays 0 till the next cycle when it starts rising again, when the switch is switched on again. So this is the inductor current waveform. The average of the inductor current is the input DC current IN. Again, this part of the inductor current is the diode current. We can plot it separately. The diode current goes to IP when the switch is switched off, and then falls to 0 at the end of TF interval and stays 0 till the switch is switched off again in the next cycle. This is the diode current. The average of the diode current is the load current again. So this is I0. So I0 equals ID average. You can derive an equation for the V0 by V in ratio here. This has been done in 2B-3. I reproduce the results here. So the V0 by V in ratio here is V in TS by 2L D squared by I0 plus 1. Notice that V0 by V in ratio not only depends on duty cycle, it also depends on the load current. Besides, it also depends on the input voltage, switching frequency or the switching period, the inductance. V0 by V in form is 1 plus something. This part is a positive quantity. So V0 by V in will always be greater than 1. I can rewrite this equation so that I0 is on the left hand side. It's easy to do. I have done that here. So I0 equals this quantity. Notice that I have V in TS by 2L here, whereas our current normalizing factor is V0 TS by 2L. So we need to multiply and divide the numerator by V0. Then we will get I0 equals V0 TS by 2L D square times V in by V0 divided by V0 by V in minus 1. V0 TS by 2L is the current normalizing factor. V in by V0 is the normalized input voltage. V0 by V in is 1 over the normalized input voltage. After a bit of manipulation, I can rewrite this in normalized form. I0 n equals D squared times V in n squared divided by 1 minus V in n. This is the last of the equations we need. I have highlighted this equation. Now we will tabulate all the equations before we plot. So first we will see the equations without normalization. For continuous conduction mode, of course, it is V0 by Vn equals In by I0 equals 1 by 1 minus D. The voltage ratio for the boundary operation is also the same. So V0 by Vn equals In by I0 equals 1 by 1 minus D is valid in this case also. And the boundary output current I0B is given by V0 TS by 2L D times 1 minus D whole square. The last one is the DCM equation. That is V0 by Vn is V in TS by 2L D square by I0 plus 1. Next we will present the normalized equations. The normalization factors in this base V0 normalizing scheme is Vn equals V0, the output voltage, In equals V0 TS by 2L as we saw. The CCM normalized equation can be written as V in N, the normalized input voltage, equals Vn by V0 equals 1 minus D. The same equation is valid for the CCM DCM boundary also. And the normalized boundary current, as we saw, equals 1 minus V in N times V in N square. Lastly, the DCM normalized equation we saw is I0 N equals D squared times V in N square divided by 1 minus V in N. Now we will plot the normalized equations so that the complete characteristics of the boost converter can be visualized in one single plot. Now the same table has been brought to the left hand side. You have the CCM, DCM and the boundary equations here, and these are the normalizing factors. We will plot V in N versus ION. The y-axis is V in N, V in by Vn. The x-axis is ION, IO by In. In this complete plot, V0 is being held constant. That means by adjusting the duty cycle every time, we are managing to get the same output voltage. So these curves that we are going to see are valid for one V0. This is the normalized boundary current, and we have already seen the plot. It looks like this. This side is DCM operation, this side is CCM operation. This is the voltage ratio equation under CCM. For every D value, this will be a horizontal line. For D equal to 0.1, V in N will be 0.9 as shown here. This is the DCM equation. If we plot this for D equal to 0.1, it will have the shape shown. The CCM line and the DCM curve will join at the boundary. Likewise, if D equal to 0.2, V in N will be 0.8. And this will be the corresponding DCM curve. This is D equal to 0.3. The corresponding DCM curve is here. D equal to 0.4, D equal to 0.5, and so on. So this represents the complete characteristics of the boost converter. Any boost converter. Now consider one operating point here. Here the duty cycle is 0.5. V in N is 0.5. That means the input voltage is 50% of the output voltage. If the output voltage is 100 volts, the input voltage is 50 volts. This operating point corresponds to an ION value of 0.25. That means the output current is 25% of the IN value, where IN value is V0 TS by 2L. Now we reduce the current. TS and L do not change. We are assuming V0 is always kept constant. Since Vin is maintained the same, Vn will continue to be 0.5. As we reduce the current, the operating point will move horizontally leftwards towards the boundary. At this point, the converter is operating at the boundary. The boundary normalized current is 0.125. The normalized input voltage is still 0.5 and the duty cycle is still 0.5. Now maintaining the input voltage Vin, let's reduce the current. Since Vin is maintained the same, Vn will continue to be 0.5. So the operating point shifts horizontally leftwards as shown. At this new operating point, the normalized output current is 0.045. So that means we have reduced the normalized current from 0.25 to 0.125 and then to 0.045. The output voltage is still the same. How is that possible? The closed loop system has changed the duty cycle. The new duty cycle, as you can see, is 0.3. So this set of graphs, particularly in the DCF side, allows you to visualize and see how the output voltage is maintained to be the same as load current is reduced by changing the duty cycle. If the output current is reduced further, the operating point will move leftwards still more and the duty cycle will reduce to 0.2 and so on. Next, we will see what will happen if you follow a single curve rather than assuming that the input voltage is maintained constant. So let's go back to our starting point. The initial operating point of the converter is here. The normalized output current is 0.25 and the normalized input voltage is 0.5. Now we will move along the deep purple curve corresponding to D equal to 0.5. As we do that, the operating point shifts to the CCM-DCM boundary. At this operating point, we are still maintaining the normalized input voltage at 0.5. The corresponding normalized load current is 0.125. As seen before, the system will set the duty cycle at 0.5. Now if we follow along this curve, we can reach this point. Here the normalized output current is 0.067 and the normalized input voltage is 0.4. So how do we interpret this operating point? What we are meaning is, if the normalized input voltage is 0.4 and if the normalized output current is 0.067, then the duty cycle will automatically become 0.5 in order to maintain the same output voltage. This curve connects the points along which the duty cycle happens to be zero point 0.5. We do not set the duty cycle at zero point 0.5. The duty cycle is set by the closed loop system. So the interpretation of the curve corresponding to D equal to 0 0.5 is it represents the operating point where D will be 0 0.5. So what is varied in the system is V in and the load current. D is a result of the system operation. Next we will do a problem to understand these characteristics better. In a boost converter, V0 equals 100 volts regulated to be constant. Fs is 100 kilohertz and I0 varies between 0.2 amperes and 2 amperes. Assume ideal operation. Calculate the minimum inductance L min such that the operation is always in CCM for these three voltage ranges. Vin equal to 80 to 90 volts, Vin equal to 20 to 40 volts, Vin equals 20 to 90 volts. This shows the voltage and current normalizing factors. The normalized boundary current equation is given by I0 Bn equals 1 minus Vn times Vn square. The current range is between 0.2 amperes and 2 amperes. We know that the converter goes into DCM when we reduce the current sufficiently. If the operation is at the boundary between CCM and DCM at I0 equal to 0.2 amperes, at all higher currents, the operation will definitely be in CCM. So that is the first thing we notice. So in all cases, we must ensure that at I0 minimum, that is 0.2 amperes, the operation is in CCM, or at least on the boundary between CCM and DCM. So the question is, at which voltage? If you take the first problem, problem A, do we take 80 volts, do we take 90 volts, or do we take a value in between? That's what we have to see in each of these three cases. First, let's take case A. V in range is 80 to 90 volts. V0 is 100 volts. So the normalized voltage value is 80 by 100, 0.8 to 0.9. We can mark the range here as shown. So at the minimum current, we want the operation to be on the boundary. Notice that I0 10 is I0 by IN. I0 is the minimum current, 0.2 amperes. IN is V0 TS by 2L. We are now doing the design. L is not fixed. We have to choose the L. So by varying L, IN can be varied. By varying IN, ION can be varied for the same I0 0.2 amperes. Let's keep the operation at the CCM DCM boundary at Vn equal to 90 volts. That is Vnn equal to 0.9. Then we have this situation. The red dot here shows the boundary operating point which occurs at Vn equal to 0.9. The corresponding IN is here. This corresponds to one value of L. This small vertical line here shows how the operating point changes when the input voltage changes between 80 and 90 volts, keeping the current constant at 0.2 amperes. If the voltage is now reduced towards 80 volts, you notice that the operation slips into DCM. So obviously, this is not the correct choice. We can next see whether by keeping the operation at the CCM DCM boundary at 80 volts input voltage, whether our problem is solved. Now we are choosing the inductor in such a way that at 80 volts, the operation is on CCM DCM boundary. The corresponding ION value is this. Here we notice that when the input voltage changes from 80 to 90 volts, the operating point goes up and goes into CCM, which is fine. So the worst case input voltage here is Vn equal to 80 volts or Vnn equals 0.8, the lowest value in the range. Substituting that, we will get the worst case IOBN. So IOBN is 1 minus 0.8 times 0.8 square, that is 0.128. So this value here is 0.128. In other words, we are planning to choose the inductor in such a way that ION becomes equal to 0.128 when the current is the minimum value 0.2 amperes. IOBN is IOB by IN. IOB is 0.2 amperes. We can calculate IN. IN is 0.2 by 0.128, that is 1.5625 amperes. And IN is TS V0 by 2L. So V0 TS 1 over 100 kilohertz, 10 microseconds. V0 is 100 volts. We can calculate the L value, which is the L minimum. So in case A, the L minimum is 320 microhenry. Usually we will keep a higher inductance. One is component tolerances. Second is we are assuming an ideal boost converter operation, and boost converter due to losses, the actual characteristics can be somewhat different. So we need to give a margin. So keep it a bit higher. So the important point is the worst case operating point occurs at 80 volts, which is the minimum voltage in the range 80 to 90 volts. Next, we will move on to case B. The V in range here is 20 to 40 volts. The corresponding V in N range is 0.2 to 0.4. And we can mark that on the y-axis, 0.2 to 0.4. Let's take the minimum voltage, 20 volts, that is V in N equal to 0.2, and locate that on the boundary. So we will have the situation shown. So in this case, we are planning to ensure that when V in N equal to 0.2, the operation is on the boundary. That means we are planning to keep the ION corresponding to 0.2 amperes at this value. Choose the inductor appropriately. Now, as you can see, if the input voltage goes up from 20 volts, it can go up to 40 volts, the operation goes into DCM operation. So this is not the right choice. Next, we will keep the operation at the boundary when V in N equal to 0.4. Here we are choosing the inductor in such a way that when V in equal to 40 volts and I naught equal to 0.2 amperes, the operation is at the boundary. As voltage goes down at the same minimum current, we can notice that the operation stays in CCM. So this is the design choice that we should make. The corresponding ION is here. The worst case V in is 40 volts, V in N is 0.4. So substituting that here, we will get IOBN as 0.096. And IOBN is IOB by IN, and again that is 0.2 by IN. So IN is in this case 2.0833 amperes. And IN is of course TS V0 by 2L. Once again we can calculate the value of L, and that is 240 microhenry, lower than before. But the critical thing here is that the worst case voltage here is not the minimum voltage, it is the maximum voltage. In case A, the worst case was at 80 volts, which is the minimum voltage. Here it is at the maximum voltage. Next, we will move on to case C. Here, the voltage range is from 20 volts all the way to 90 volts. So the corresponding V in N is 0.2 to 0.9. We can mark this range on the y-axis as shown. Now we will try the same tricks as before. First, we will take the minimum voltage. Here we are choosing the inductor in such a way that when the input voltage is 20 volts and the current, output current is 0.2 amperes, that is the minimum value, the operation is on the CCM-DCM boundary. If we do that, then this will be chosen as our worst case operating point. In this case, you can see that if the input voltage goes up about 20 volts towards 90 volts, we will be moving into DCM region. So this solution is not acceptable. Next, we will place the higher voltage 90 volts at the boundary. Here we are choosing the inductor in such a way that when the input voltage is 90 volts and the load current is 0.2 amperes, that is the minimum value, the converter operation is on the CCM-DCM boundary. Here we notice if the voltage goes down now from 90 volts towards 20 volts, the operation again moves into DCM. So this solution is also not correct. So choosing the worst case as 20 volts does not work. Choosing the worst case as 90 volts, that also does not work. So we have to stay clear of the DCM region here. We will move this vertical bar to the right so that it just touches the boundary curve as shown. Now it touches it at the peak point which we have determined earlier. So this is the peak point M. Corresponding to that, the V in N value is 2/3. We have seen that before. The actual input voltage corresponding to this point is 66.7 volts. If we choose that worst case operating point to be at V in equal to 66.7 volts, if the voltage goes higher towards 90 volts, we are only moving into CCM, which is okay. Likewise, if the input voltage goes lower towards 20 volts, again we are moving into CCM, which is perfectly all right. The worst case operating point in this case to ensure CCM operation under all design conditions is V in N equal to 2/3, that is V in equal to 66.7 volts. The corresponding boundary current value IOBN is the same as IOBN max, which is 0.1481. We have determined this earlier. And IOBN is IOB by IN. IOB is the minimum load current, 0.2 amperes. So IN can be shown to be 1.350 amperes. And IN is of course TSV0 by 2L. We can calculate the L as before. And if you calculate the L minimum, it is 370.4 microhenry. So in this case, a higher value of 370.4 microhenry has to be chosen. The main point here is that the worst case here is neither the minimum voltage of 20 volts nor the maximum voltage of 90 volts, but the in-between voltage of 66.7 volts. You can see that the worst case operating point very much depends on the voltage range. If the voltage range covers this maximum boundary point, then you should choose the maximum boundary point. Otherwise, the value closest to the maximum boundary point should be chosen. If you want to avoid this problem altogether, just avoid operating in this shaded area totally. Just limit yourself to this. You will always be in CCM. So in other words, if you choose 370.4 microhenry, that will cover everything. If you assume that at the minimum current, ION equals 0.148, from there you calculate the L and then give some safety margin to account for non-idealities and for component tolerances. The operation will always be in CCM, irrespective of the input voltage variations. We have seen how the visualization of the complete characteristics helps in understanding the design of the converter. Suppose instead of CCM operation, we want to keep the complete operation in DCM. Then how would you go about it? In some cases, Because of dynamic response issues, people may not prefer to operate a boost converter in CCM. They may prefer to operate it in DCM. In which case, how will the inductor be chosen? That is given as a homework problem. In a boost DC-DC converter, V0 is 50 volts regulated to be constant. Fs is 80 kilohertz. I0 is 1 amperes to 3 amperes. Assume ideal lossless operation. Calculate, in this case, the maximum inductance, L max, such that the operation is always in DCM for these two V in ranges, 30 to 45 volts and 25 to 35 volts. With this, we have come to the end of this video. In this video, we put together the complete characteristics of a boost DC-DC converter under CCM, under DCM, and under the boundary condition between the two. We saw the characteristics in graphical form and understood how to interpret the graph, and then used a design example to understand the graphical representation in greater depth. In case you like this video and this series of videos, please consider subscribing to this channel and clicking the like button. Thank you.